Figured I should show it to you in advance of the exam. You will be permitted. You need to turn it in with your exam. It'll be graded carefully. As it says, no worked out examples. You've seen this before in discrete, all those other courses. Same deal.
You don't want the graph theory?
Don't believe so, but there aren't as many formulas to run through that one, are there? Everything seems to come back to one formula, really. Handshake theory. I don't have very many other formulas at this point. Ask me at exam 2. No, but you should read something.
Absolutely, that's scary to me.
As everybody sees it. No, today you just are giving me the last material. The exam is Thursday. See, it even says so. Thursday.
You're visible.
Quick, this will be what I want to do today is combine the two courses that some of you are taking with me. Let's consider an arbitrary group and for any element in the group, we can create the subgroup generated by A. That's great. How do I generate this? I repeatedly apply A. Whether that's addition or multiplication, I just do that over and over and over. So we write either this, or if we wanted to use additive notation, we could think of getting multiples of A. So A plus A plus A plus A is 3A, and so on. What if instead of starting with one element, started with 2? If I start looking at this, what sort of things am I going to get? Not a rhetorical question.
You have to take like generate a subgroup of both and then take the union.
If I were to do that, I would see any expression that looked like A to some power, whether that power was positive or negative, and I'd see any expression of the form B to some power. whether that power was positive or negative. But that's not a group yet, because that set, the set containing just those things, isn't closed. What else could I have? If we consider A and B as letters, what other words can you make? You said I can make A and B. What other words can I make? I gotta have products in there, right? Between A and B. So I can't just use the union of the things generated by A and the things generated by B. I have to look at all possible combinations, right? A to the I, B to the J, right? But I don't know that this is abelian. I'm using multiplicative notation. It might not be abelian. So I might actually have A to the I1, B to the I2, A to the I3, B to the I4, and I might not be able to regroup that. I mean, even if I wrote A, B, A inverse, which is still a possible word, that may or may not be equal to B. If my operation turns out to be commutative, then all of these sorts of things reduce to things that look like this, because I can just switch until I grouped all the A's together and grouped all the B's together. But I don't know if that works. So you could think of making words of any combinations of A's and B's, and A inverses and B inverses in any order you want. Cancel out any things that are inverses next to each other, and combine anything that is the same letter next to each other. But that's going to give you a string that kind of looks like this with as many repetitions of A's and B's as you want. That's a much more complicated looking thing, unfortunately, isn't it? How do I know this is a subgroup?
It's closed.
Okay, that's one. What other things do I need?
I mean, if it's a subgroup, then it, and G is a group, then it inherits the associativity.
It definitely inherits the associativity because it's a subset. But I'm trying to prove it's a subgroup. If I know G is a group, then H, is whatever this set is of all these things, definitely inherits the associativity. I'm good with that. What else do I need?
And inverse into identity.
But I got to do those in the other order because I have to have the identity so I can do the inverses. But if everything generated by A is in there, then A to the 0 is in there. And that's my identity. Check. Does everything have an inverse? What would be the inverse of this thing? No?
B to the negative J and A to the negative I.
In that order, because you'd want the B parts to be next to each other, and then they go away, and then the A parts are next to each other. So that's correct. And the same thing here. I need B to the negative I4, then A to the negative I3, B to the negative I2, A. So I can do all the inverses. The subgroup establishes all four of my properties. It could be that this is the whole group, but I don't know yet. Do you have a question?
Yeah, for the identity, we'd be looking at the identity equals 0 first because it's exponents being multiplied.
Would be A to the 0.
A to the 0, yeah.
And that's the identity E.
Okay, yeah.
Yeah.
Right.
And since these are in there, I get the E.
Okay.
You're welcome. And now I have the opportunity to generate a group from a set, as opposed to just from one thing. Cyclic groups are generated from one thing. But now I have the opportunity to think about what can I do with two things. What's a group you already know is not cyclic?
The Klein group.
A Klein 4 group. There's my Klein 4 group. So that means it can't be generated by one thing. But when we showed this wasn't cyclic, we said, what if you took two things? You have to have E and one element to get something, but what if you took E and two elements? Pick any two other than E.
A to Z.
I know that if I take A times A, I get E again. So E is in the subgroup generated by A and C.
I say C times B.
Oh, B's not in here.
AC.
Ah, A times C is B. So B is in the thing generated by this. Which means the Klein 4 group isn't itself generated by one thing, but it can be generated by two things. And it turns out it can be generated by any two non-identity elements. Because if you had A and B, what's AB? If you had AC, you get B. What if you had BC? BC? Which gives me the other element.
Oh, that's A.
Yeah, sorry. Yes, everything only appears in each row once, and each row and column once. That's got to be an A. C's already there. Oh. A group that has a finite set that generates it is called a finitely generated group. Notice the group itself does not have to be finite to be finitely generated. The integers are cyclic. They have a single generator, but the group itself is infinite. Dihedral groups. There was an example of a dihedral group in the homework big table, ugly thing with U and row, so that we could think about the options that went out. Was it D4 or was it D3? The example we did for here we go. Dihedral groups. Chapter 4. We have the dihedral group for the triangle. These 6 things could be thought of as you pick the triangle up, you move it, you set it back down. What are your symmetries? And we had a rotation. Okay. 1 goes to 3, 3 goes to 2. We twisted our triangle. If you twist it twice, if you twist it and then twist it back, you get the identity, which is pick it up, put it back down, and go anywhere. So there's our E, and then 2 rotations, a rotation by 120 degrees, a rotation by 240 degrees, and then 3 mirrors. This mirror switches 1 and 2 and leaves 3 fixed. Looking at me like I've never shown you this thing before. Remember that? So, if I name the things in this group, I'm going to name that cycle 1, 2, 3. I'm going to call it rotation. Then this is rho, and this is rho squared. This one that leaves 1 fixed switches 2 and 3. I'm going to call that mirror, mu. This is the mirror rotated 240 degrees because it leaves 3 alone. This is the mirror rotated 120 degrees. So I can build these out of each other, which means that my dihedral group can be generated from 1 rotation and 1 mirror. And really, it's whichever mirror you want to use, and whichever rotation you want to use, as long as it's by the smallest possible angle. Whether you go clockwise or counterclockwise doesn't matter. We did cyclic groups, right? Z6. Generator for Z6. Absolutely. But there's more. Five. Because those are the 2 numbers that are relatively prime to 6. But consider for a moment this set. Neither of those are relatively prime to 6. On their own, I couldn't make Z6 out of this. But what's 2 plus 3? Which means as soon as I have those 2, I have 5. As soon as I have 5, I have everything, don't I? Sneaky. But I could also do it directly, right? 3 minus 2, because if I have 2, I have its inverse. 3 minus 2 is 1. 2 and 2 is 4. 1, 2, 3, 4, 5, I got them all. Oh, 0, 3 plus 3. So I can generate all of Z6 from these two, which means it's cyclic, but it's also generated by other things. However, what if I use 2 and 4?
Leave 2 for 0.
Aha. So in spite of the fact that I have a generating set of size 2, I'm not guaranteed that any size 2 set will work. There's got to be more to it. Consider Z18 for a moment. And let's consider what can we generate using 8 and 10.
You won't be able to get the evens.
Why?
Because if you take 10 and 8, subtract, you get 2, and then 2, 4, 6, 8.
I get all the even ones, right? And if I look at what was generated by each one, 8, the greatest common divisor of 8 and 18 is 2. So I would expect to get 9 elements, all the even ones. The greatest common divisor of 10 and 18 is also 2. We expect to get all the even ones. Now I'm looking at just what can I do with each one. When I start combining them, I'm stuck in the same process. So I only generate pieces. So if I'm doing this with intersections, if I'm thinking about where the overlap is, and I'm thinking about what the smallest bit is, it's the smallest thing I can make, how do I create this idea? I need a set theory idea for a second. I want to write, I have a collection of sets. I don't know how many there are. For the record, most of the time I'm dealing with finite things, so I would be some finite index set. Maybe 1 to 10 or 1 to 100, 1 to n. But it could be an infinite index. It could be countable or uncountable, it doesn't matter. I have some way of indexing my sets. I am going to create this. I've seen this before. I know I have.
Is that, and I could be remembering wrong, but is that the equivalent to like a summation symbol, but for multiplication?
Unfortunately, no, the multiplication version is a pi for product. S for sum, P for product. That's an intersection. So what I'm defining is the intersection of all of these sets, but that could be an infinite intersection. I want you to take all of these. So I'm going to define it as whatever elements are in all of these sets at all at the same time. So literally, it's the middle of the Venn diagram. But I've got a crap ton of sets, and it might be very hard to draw a picture that way, so I'm not going to draw it. Why would I create such a unquestionably sucky looking thing? Paper keeps moving on me. If HI for each I is a subgroup, then the intersection of all of those subgroups is again a subgroup. That's what that less than symbol means.
After that.
I started to draw it, the intersection, but it shifted the paper on me, so it screwed up, so I just scratched it out. It's garbage. It's garbage, throw it away.
This is sort of related. It just occurred to me that whenever we write something as less than, are we saying that it's a subgroup?
That's our symbol here for subgroup, yes.
Right.
But that's why the union didn't work, right? Just the A's, just the B's wasn't enough. The intersection is what I need because I need for the overlap to happen. So I can think of doing this intersection as looking at the smallest pieces. And then I look at what those generate. And this parallels our definition for the smallest subgroup containing A. I can now say the smallest subgroup containing A and B be the subgroup generated by those things. So the way we described this set at the beginning, where we said what we really need is to take all the possible power combinations of AIs. That's exactly what we want. And each AI could appear at multiple different places in the product because we don't know whether or not this is commutative. And those integral powers could be positive or negative, depending on whether we're taking the element or its inverse. But then all of our other rules apply. If I want the inverse, I have to reverse the order within that multiplication. All of that works the same. So how do I keep track of what's going on with my generators? And how do I figure out if I get the whole set or not? That's my next step. Questions before I get to there? Let's consider a small group, Z6. It's going to be my example starter. I want to think of the operation I am using as an action on that set. What I want to do is I want to make a digraph. A diagram? What? Chapter 9, Section 3, discrete. The digraph of a relation. This diagram that I'm going to build shows what elements are related by the action of our group. But we're only going to use the actions of the elements in our generating set. A digraph takes elements of our set, in our case our group, and joins them with arrows, which are also called directed edges or arcs. So if I had two items, group element 1, group element 2, I could say, oh, we go from group element 1 to group element 2. The edges are going to represent what happens when we use one of our generators. Which means if we have more than one element in my generating set, I'm going to need more than one kind of arc. I can color code them, I can style code them, I use solid lines, dotted lines, dashed lines, all sorts of ways of telling my edges apart. But I said I was going to start with Z6 as our example. So let's consider Z6. The elements of Z6 are 0 through 5. Make a picture of 0 through 5. I don't care what picture you use. You could make a hexagon. You could put them in a straight line. You could put them in any order you want. I'm going to start with the fact that I know this group is cyclic, and we know we have a generator. Pick a generator. Want to use 1 or 5?
1.
There are the elements of Z6. Where do we start? Well, I'm using the generator 1, right? Add 1, what do you get? So your arrow goes from 1 to 2. You're now on 2, what do you get?
3.
Look, it's a cyclic group because it's a cycle. Went around the loop. But what if I'd used 5? I'd go the other direction. Because 5 and 5 is 10, but in Z6 that's 4. 5 and 4 is 9, in Z6 that's 3. 5 and 3 is 8, but that's 2. 2 and 5 is 7, that's 1. Now it's a cycle the other way. So in one sense, I can think of going around my clock, clockwise or counterclockwise, depending on where I started, right? What if I change generating sets? We also showed that Z6 could be generated with both 2 and 3, right? But here's the deal. I'm going to need 2 kinds of arrows. I'm going to need an arrow for 2 and an arrow for 3. Because they do different things to my elements, don't they? So here's what I need you to do. You want this color to be 2 or 3? All right. So over here, I'm going to make a note that this color represents 2, and then this color represents 3. If anyone here cannot tell those two apart, that's fine. What you could do is you could make this a dotted instead. Then you'd have a solid versus a dotted, and we wouldn't have to depend on color. We're starting with 2 or 3. Starting with 3, pick a number. 3 plus 3 is? Which is 0. So from 3, I go to 0. 0 plus 3 is? So I go back to 3. We missed some things. So pick another element. 1 plus 3 is 4. 4 plus 3. I'm still missing things. 2 plus 3 is 5. 5 plus 3 is 8, but I'm in Z6. That's horrible looking. Let me rearrange. I'm going to put the numbers in pairs. 0 with 3, 1 with 4, and 2 with 5. And now, 0 goes to 3, 3 goes to 0, 1 goes to 4, 4 goes back to 1, 2 goes to 5, and 5 goes back to 2. I've color-coded the action of 3. Now, back to 2. I need to do both generators. You see, I haven't gotten the whole group from any of this, have I? How do I get the whole group? Let's use 2. What happens with 2? Pick a place to start. 1 and 2 is?
3.
So 1 goes to 3. 3 goes to? 5 goes to? So I get a group there. Well, I get a loop. Pick another place, because I missed some stuff. So if I start with 2, 2 goes to 4, 4 goes to 0, and 0 goes back to 2. So what this tells me is that I screwed up the way I lined these up. I shouldn't have done 0, 1, 2, 3, 4, 5. I should have done 1 and 3 and 5 on the same side, and 0, 2, and 4 on the same side. So let's rewrite this again. Promise there's a reason. I'm just switching the middle pair. Now let's put those arrows back in. 1 goes to 3, 3 goes to 5, 5 goes to 1. 4 goes to 0, 0 goes to 2, 2 goes to 4. But those are just the one color arrows. I still need the other color arrows. Notice those go back and forth between the same things. 0 goes to 3 and 3 goes back to 0. Instead of drawing 2 arrows, let's just draw an edge without arrows. Then we can say, oh, that one goes both ways. That one goes both ways. So now what I have is I have a different picture. But it shows me the relationship that's going on between all of the elements and the elements of my generator. So if I want to ask, you're using 2 and 3, how do you get 5? Oh, you have to go from 2 to 5 using a 3, right? How do I get from place to place? How do I make the elements? I can figure out what's going on using these as a generating set. By the way, you absolutely could write this picture in a different way. What if I made 2 triangles? What's your picture look like that?
The arrows connecting 1, 4, 2, 5, 0, 3.
Okay, but those should be those, right? The blue ones, and they should be really not arrows, they should be dashes because they're undirected. You go back and forth. But then the arrows, exactly. 0 goes to 2, 2 goes to 4, 4 goes back to 0. 1 goes to 3, 3 goes to 5, 5 goes to 1. Which is the picture in the textbook on page 73. Only instead of using blue and orange, they use solid and dashed. Because it's a black and white picture. This is a Cayley digraph. Arthur Cayley developed this idea to visualize a graphical version of group behavior.
Like, say you have to go from 0 to 5, would you just do, or would you, say that it's like, you add it, you go from 0 to 3, then 3 to 5?
0 to 3, 3 to 5, or 0 to 2, 2 to 5, right? As long as there's a path, I know I can get that element. I have the identity, I have my two generators, how do I get all the rest of them? I follow the arcs. Every Cayley digraph satisfies 4 properties. The digraph is connected. Why does this have to be true?
Wasn't connected, it wouldn't be closed.
I'd have a section over here, a section over there, and I'd have no way to get from one to the other. Oops, I couldn't get some things out of my group. If I'm getting the whole group with a finitely generated set, I've got to have connectivity. Now, because our example is abelian, I haven't really specified whether my action is occurring on the left or the right. So it's up to us to make that decision for non-abelian behavior, whether we want to do it on the left or the right. The default in the book is to work on the right. So if I think about this for non-abelian behavior, I want to think about the right operation. So it's the left operation. Why can there be at most one arc between two elements?
That would break our, our rule of, onto or, not onto, the other one.
One-to-one?
Yeah, that mess with that.
Kind of, but not in the way you're thinking.
Okay.
Because we're not actually looking at a function here. And so that one-to-one operation, that's our isomorphic behavior. It's the right idea, kind of. But that, yeah, I don't have that function here. Let's consider what this means. If there's an arc from G1 to G2, then there's something that I can say, hey, G1 times something. Notice I put the G1 on the right, using the right multiplication. Has to be equal to G2.
So is that like saying that one can't generate more, like, you can't generate something that you can't, I don't know how to word it, but
And that's why I'm not quite sure what you're saying, Colin. So keep
Yeah.
talking at me. Keep talking at me.
Like if you have more than one arc going to like a number, say, you can't necessarily generate it with that number, right?
Well, but up there I've got an arrow from 2 to 4, right?
Yeah.
I've also got an arrow from 1 to 4.
So those two can generate 4, right?
I can make 4 from
Yes.
2 and 1, yes.
But, well, never mind. Because you would be able to, well, if you have, yeah, because you can't generate 5 from just like 2 and 4.
There's no arc from 4 to 5, right? Because I can't solve something plus 4 equals 5 using 2 and 3. If there were more than one arc, then there would be 2 different solutions to this equation. If X is in the generating set, if I want to get from 1 to 5, I've got to go through, if I want to get from 4 to 5, I've got to use 1. 1's not part of our generating set. We were generating with 2 and 3, which means there's no arc from 4 to 5. If there is an arc, then this element is in my generating set. Why can't there be more than one arc? Because that solution is unique. Otherwise, we wouldn't have unique inverses. We're in a group, so we have a unique solution. So, I'm connected. There's at most one arc between things. By the way, if it were that there was an arc between everything, then we'd have a huge number of generators, wouldn't we? If I can go from 1 to 2 and 1 to 3, then both 1 and 2 are in my generating set. If I go from 1 to 4, then 3 is in my generating set. 1 to 5, oh, I'm going to have a lot of generators here. So these are actually very sparse graphs most of the time. Few edges. Property 3. For every element in the group, there is a unique arc in and out of that element in each color. Each flavor, each style, corresponding to each generator. Go back and look at our Z6 group. 4. There's an orange arrow into 4 coming from 2. There's an orange arrow out of 4 going to 0. There's a blue arrow out of 4 going to and in to 4 from 1. And no matter what number you pick, there will be, for our set, there were 2 generators. There'll be 2 outs and 2 ins. If I had 3 generators, each one would have, each number would have 3 outs and 3 ins. If I had 5 generators, I'd have 5 outs and 5 ins. Since we're trying to look for small generating sets, it's unlikely that I'm going to do something that big, but there are places where using larger generating sets is helpful. We won't touch most of those. Most of those occur when you look at groups of functions or groups of matrices, at which point your generating sets become infinite. I don't want to do a digraph on an infinite set. Questions? Let's suppose that there were 2 different arrows that both went from 1 to 7 in whatever group I'm working with. But that means those go from the same start to the same end. Then if I picked another number, let's say 1 to 7, let's say I went from 2 to 8, well then both arcs should go from 2 to 8. If one of them does, the other one has to. It means those 2 generators parallel each other exactly. It means they generate the same thing. Why would you do that? One of them is redundant. So if my goal is to have a nice generating set, probably want to use as few as I can get away with, I don't want parallel trails marching around my digraph, parallel walks.
Give an example of like a time where there'd be the 2 generators are parallel.
So let's suppose I did in Z18, I did 2 and 4. Greatest common divisor of both is 2. They're going to generate the same group, aren't they? One will do it by going every 2. One will do it by going every 4.
So every other would have 2.
And they'd be going the same places, kind of. It's much harder to do in these groups. It's easier to do in the dihedral groups. Those are very complicated. But what that really means is if I were to see something that looked like this, nice loud colors. As soon as I see that, I know there's something wrong. If both of those arcs are in there, then those 2 generators are behaving the same. And that means somehow I used 2 twice. Shouldn't be doing that. The smallest example I can think of where this works is D4. So imagine you've got the rotations on a square. So you could think of the action of rotating by 90 degrees, right? But you could do that either clockwise or counterclockwise. If you did it clockwise, you'd have a permutation, wouldn't you? We call that rotation. But let's say instead of using that as rho, I did the 180 degrees. And I said, I'm going to do 180 degrees clockwise. And somebody else says, I'm going to do 180 degrees counterclockwise. Don't both of those end in the exact same place? Every time, no matter what you do from wherever you are, if you rotate 180 degrees clockwise or 180 degrees counterclockwise, you're going to end up in the same place. You only need one of those as generators, not both. Knew I could find an example. White balance, thank you. More questions? So, I knew the operation. I knew what the generator was. I was able to build the picture. What if I start with the picture? Here's my diagram. From E to A squared to A cubed back to E. From AB to B to A, those arrows go the other way. And then there are dotted lines. Dotted lines don't have any arrows on them. It means they go both ways. Yeah. All those dotted lines, because they are unoriented, they're not arcs, they're edges, if I want to be pedantically graph theoretical about it, then they go both ways. You could put both arrows if you wanted. I think it just clutters up my picture. I don't know what this group does. It's got 8 things. I don't know what it does. How many generators are being used in this? Because there are 2 different kinds of edges, the solid edges and the dotted edges. What are my 2 generators? Because if I start at the identity and I take one solid arrow, I've gone to A. If I start at the identity and I take one dotted arrow, I've gone to B. So this is a finitely generated group. The generating set is 2 things. If I want to do A squared times A cubed B, what do I do? What the? If I want to know what's going on this group, I do multiplication on the right. So if I do A times AB, start at the vertex A, and then I do AB, which means I follow the solid arrow for A and then the dotted arrow for B. So I start at A, and I go AB, and I end up here. So A times AB is A squared B. That makes perfect sense, doesn't it?
So, can you just do that one more time?
Sure.
So, like, why wouldn't it go to AB on the diagonal?
Because it says A times AB. And I'm working left to right this time, not right to left. I'm working left to right. So start at A, then do A, then do B.
Right.
So do A, then B. Remember, that's what that solid edge means. That solid edge means I did A.
Okay.
So I went from here to here to here. If I start here and I do B, then I go here.
Is every Cayley diagram example always left to right?
Because we decided we were doing multiplication on the right. So it's going to depend on what book you're looking at. In this book, yes.
So if this is multiply on the left, you go right.
I'd go the other way. I'd go this way. I'd write it in the other order. And I would say, oh, you've got to go that way. Like our permutations do.
Yeah.
So it depends on how they tell you. This textbook said we're doing it on the right. So now I could ask, what is this group? It's a group of 8 things. I don't know what it is. Is it cyclic? Not according to this picture. But we saw that in Z6, right? The picture I had with Z6 had a triangle on the outside, a triangle on the inside, and stuff connecting it. But it's also cyclic. Oh. What I really need is a table for this entire group. So then I could figure out, like if I had the table for Z6, I'd be able to say, hey, look what happens when you look at the row containing 1. What happens when you look at the row containing 5? I could find the generators. If I could find one element that repeatedly using it gave me the whole group, I'd be able to figure out what's going on. What happens when you multiply by E?
Get the same thing?
There you go. I built the table. And I filled in the first row and the first column. Now I decided I was going to use the outside square first and then the inside square. So I wrote my elements, a squared, a cubed, and then b, ab, a squared, b, a cubed, b. If you write them in a different order, that's fine. It doesn't matter. But now I want to fill in the second row and the second column. It's probably easier, since I'm multiplying on the right row column, let's fill in the column. So, AA should give me an A squared. A squared with an A on the right should give me A cubed. A cubed with an A on the right. A cubed with another A gives me E. I'm going to use this to fill it in. So what happens when I have B? Say again?
Move to the inside picture.
I'm starting at B.
Oh, right.
And now I put an A on the right. That should give me BA. BA is not up there. So what the hell is BA? Start at B, move in the direction of the A arrow. BA is A cubed B. Holy crap, I figured something out here. That is what's going to go here. Start at AB. So now I would be doing ABA. Where do I end up? Here. Start at A squared B. A squared B, A on the right is here. Start at A cubed B, A cubed BA, A squared B. This is clearly not an abelian group. Multiplying on the right is not the same as multiplying on the left. I can fill in every column, one at a time, all the way through this. Is it easy? Hell no. Is it doable? Yeah. Follow the arrows carefully. And eventually, okay, if I start at a squared and I do a, what should I get here? Start at a squared and do a squared. I'm doing a squared. Aha! Because then I have to follow this twice. I'm at a squared and I go a. I'm at a cubed and I go a. I'm at b and I go a. I'm at AB and I go A. I can figure out my multiplication pattern from here. With a little bit of time. I get this. This file, because I've typed it up so nicely, is posted on our Canvas page. I'm not dumb enough to do all of this work and then just hide it from you. But notice what we see here. I see something up here. This upper left corner is all A's. This lower right corner is all A's. And these two corners have all the B things. But they're not symmetric along the diagonal. This can't be abelian. This isn't Z8. This isn't Z4, Z2 somehow multiplied together weirdly. This is a weird group. It turns out this is D8. This is the rotations and the mirrors. A is the rotation by 90 degrees, clockwise, counterclockwise. B is the mirror. It flips 1 and 2, 3 and 4. How would I have no idea how I would expect you to know that. We would have first had to build the table for D8, then build this table, and then show an isomorphism between them. That's disgusting. But just looking at the digraph, I know exactly how this group behaves. I am a very visual person. And so to me, seeing this gives me more hope that I can figure out what's going on in a given group. On the other hand, that certainly isn't an easy thing to do. That's also why it's not on the exam on Thursday. But this is your reminder for Thursday's exam. You weren't here when I came in at the beginning and said it up there. Now you have it. I will see you all then. Have a wonderful rest of your day.